Okay, so both of our examples so far have dealt with kinetic friction, so let's do one that deals with static friction. Okay, so example 2.4.3 says, the figure below shows two blocks joined with a rope that runs over a pulley. The mass of M2, so this hanging mass right here, is 5 kilograms. Excuse me, while the incline is at an angle, of 35 degrees with the horizontal. If the coefficient of static friction between M1 and the inclined plane is 0.25, determine the largest possible mass that M1 can be such that both blocks remain in equilibrium. Okay, so I'm going to start by just drawing free body diagrams, right, of both of our objects. I'm going to start with my inclined plane here. Okay, and we know with our inclined plane that it's raised at 25 degrees. We also know that the coefficient of, not kinetic, sorry, the coefficient of static friction is 0.25. Okay. We have M1 that is sitting here on our incline. Okay, we're going to have that force of normal that is perpendicular to the surface in this direction. We're going to have the force of tension that's acting in this direction. Okay. We're going to have some force of static friction acting in this direction. And we know we have gravity that acts straight down, right? Which we can break up into those x and y components. So notice my x component is going to act down the hill, where my y component acts straight down. Okay, and that's your free body diagram for M1. For M2, it's a lot nicer. For M2, we know M2 is 5 kilograms. We know we have force of gravity that's going to act down. Okay, and we know we're going to have some force of tension that acts up. Okay, remember, we're looking at this to be in equilibrium. Okay, so what I'm going to do is let's look at the block on the horizontal first, right? For it to remain in equilibrium means that if we look at this x direction right here, means that it's not going to move, right? So if I look at the F net of mass 1 in the x direction, it has to equal 0, okay? And in that direction, you'll notice we have the force of tension minus that force of static friction. Okay, so in this case, we know that the force of tension in the rope is going to have to equal that force of static friction. Okay, now looking at this guy, we also know that this guy is not going to move in this direction, right? It only has one direction, and it's the y. And if we look at his F net, we also want it to be 0. So that means that the force of tension in the rope, subtract that force of gravity, has to equal 0. So the force of tension in the rope is simply going to be this force of gravity that acts on that block. And we can actually go and solve for what that is, right? We know the mass, we know what gravity is, so we can go and actually solve for the force of gravity and therefore the force of tension in the rope. Okay, so the mass of our object is 5 kilograms, and gravity is 9.8 meters per second squared. Okay, so we get the force of tension to be equal to 49 newtons. Okay, so remember what else that means for us. This rope is joined over a pulley, and all the pulley does is change the direction of that force of tension. So if we know this force of tension is equal to 49 newtons, so is this one. Okay, so we know our force of static friction is also going to have to equal 49 newtons in order for neither of those objects to move. Okay, but now we have to go and look at mass 1, right? Remember what the force of static friction is equal to, right? The force of static friction is equal to that coefficient times Fn, right? And remember, in this case, Fn does not equal Fg. Ooh. And actually, sorry, I did not solve for Fnet correctly here. Let me apologize. Let me go back here. We can still use that force of tension in the, from the other guy. We are going to need that. But I did forget one thing. There is one other force that acts in the x direction, right? This force of gravity does as well. Right? So we also have to subtract the force of gravity that acts on the object in the x direction. Okay, so what that means is the force of tension has to counteract both of these forces. So it has to counteract that static friction plus the force of gravity in the x direction. Okay, the force of static friction is mu s times that force of normal, coefficient of static friction times the force of normal. Okay, force of gravity in the x direction, if you look here, it is going to be opposite because remember your angle sits up in here. So that's where your 25 degrees sits. So the x is opposite that, so we're taking the force of gravity and multiplying by sine theta. Okay, remember, like I was trying to say there before I realized I messed up, Fn does not just equal the force of gravity in this case, right? We have to look in that y direction, and the only two forces that are present in this direction are the force of gravity in the y direction and the force of normal, right? So we know that the force of normal for this guy is going to equal that force of gravity in the y direction. Okay, and that's what I'm going to solve or sub in down here. So we know this is coefficient times the force of gravity in the y direction plus our gravity in the x direction. Okay. So we get the coefficient. The y direction is going to be gravity times cos theta. Okay, and we still have that x component of gravity times sine theta. Okay, now make your substitution for what gravity is. Gravity is mass 1, because that's the mass we're looking at here, times gravity times cos theta, plus again, mass 1 times gravity times sine theta. Okay, so just like we did last time, remember, we know what the force of tension is. We know that force of tension is 49 newtons. We've already solved for that. We know the coefficient. We know the angle. We know gravity. So we just need to solve for M1 now. So I'm going to factor out that mass, which leaves me with the coefficient times gravity times cos theta plus gravity times sine theta. Okay, so if we have that equal to 49 newtons, we're solving for M1. So M1 is going to be 49 newtons divided by all of this. mu s times gravity times cos theta plus gravity times sine theta. Okay, again, I'm going to simplify it one more for us. So that means it's 49 divided by, factor out gravity, and then it's the coefficient of static friction times cos theta plus sine theta times gravity. And that's the maximum mass that M1 can be. Okay, we have all these, so now let's just go plug them in and solve. Gravity is 9.8 meters per second squared. The coefficient was 0.25, and that's multiplied by the cos of 25 degrees plus the sine of 25 degrees, and that's all dividing 49 newtons. Okay, so I'm just going to simplify that second term. So we got 49 newtons divided by gravity times, this works out to be I get 0.649195 and so on. I'm just going to use that entire value and multiply by 9.8. So I get 49 newtons divided by 6.361 meters per second squared, which gives us a mass of 7.702 kilograms. Okay, so the maximum possible mass M1 could be, so that these stay in equilibrium, are 7.7 kilograms. Okay, and really when you look at it, this is the only mass. Sorry, that's kind of the one wording with this question that I don't like, is it's right from your textbook and it says determine the largest mass. And really this is the only mass that's going to allow it to stay in equilibrium, right? As soon as M1 becomes smaller, then this force of gravity is greater, so everything's going to move in this direction, right? As soon as M2 or as soon as M1 becomes bigger than that, then it's going to start to move in the other direction, right? So that's what you want to think about in this case. It's just a little bit worded weird, but that is the mass that's going to allow this situation to stay in equilibrium for us. Okay? This is Wanny signing off, and may the force be with you.